Hello and welcome to LFI Educates. In this video, we shall start with this force on a current carrying conductor placed in a magnetic field. Now, if we keep a current carrying conductor in a magnetic field, we know that the current, when it will flow in a conductor, then the charges are moving in the conductor. In the earlier topic, we have discussed that a charge, if it is allowed to move in a magnetic field, then it experiences some force. So here in a conductor, many charges will be there. So this conductor, how it will behave? Suppose if we take a cylindrical conductor like this, if you place it along your x-axis, it is a positive x, this is a negative x-axis, this is the axis. If you place this conductor of length L, suppose say, carrying current I in a magnetic field, let us take the electron here, negatively charged electron present in the conductor. Then the magnetic field, suppose it is passing this way, inclined at an angle theta with the axis of the conductor, suppose theta. Then we know that the electrons, they travel with a velocity in the opposite direction. We call this drift velocity Vd. Like this, many electrons will be there inside the conductor. They will be traveling along the conductor when you pass current through it. And the direction of current and the velocity of the electron, they are opposite to each other. Suppose n electrons are present inside the conductor. We will first find out for one electron, and after that we'll multiply with all the number of electrons present inside the conductor. So what will be the amount of force experienced by the conductor? Let us see. We'll start like this. Let a conductor of length L carrying current I and area of cross section of this conductor, let us take it as A. Area of cross section A placed in a magnetic field B, inclined at an angle theta. Also, let n be the number of electrons per unit volume of the conductor. And as we have discussed, n is the number of electrons per unit volume, number of electrons, n per unit volume of the conductor. Volume of the conductor will be length into area, or A into L. We can write L into A. The number of electrons will be n times L into A. You should know like this. Small n represents number of electrons per unit volume. This is volume. But when we say number of electrons, then we multiply these two, cross multiply n times L into A. Now, we know that the force experienced by a single charge, how much it will be? Already we have discussed earlier. Force experienced by a single charge placed in a magnetic field F is equal to magnetic force is Q times V cross B. V cross B. This is the formula, and this is now the charge by taking electron. So E velocity will become drift velocity Vd magnetic field will remain as it is, and sin theta will come because it is cross product. So E VD B sin theta, that will be the force experienced by one charge. Here let n be the number of electrons per unit volume of the conductor, and Vd the drift velocity of the electrons. It's much better, right? These things you have to know in advance. Now the force experienced by a single electron in the conductor let us write it as F dash. This is for one electron. Then your formula will come straightway like this: E VD B sin theta. Like this will come. But how many electrons are there? Then you can see here number of electrons present in the unit volume of the conductor is NLA. So we'll write this one. Therefore, the force experienced by the conductor is, let us write this F by all the electrons. Here we will not put dash, it is for the whole conductor of length L and area of cross section A. N times, N is the number of electrons in the conductor. E, it will be F dash. Then N, the number of electrons, you can see here, number of electrons per unit volume, A times L, and F dash is E VD B sin theta. Here you can write and keep, where N is the number of electrons in the conductor, number of electrons in the conductor. So now here this one NEAVD. You know what it represents? B NEAVD, and L B sin theta. B L sin theta remains here, and this is the expression of electric current. In the classical theory of electricity, we have come across relation between electric current and drift velocity. This is the expression that we can use here. So this one will represent, we can represent like this: F equal to I times BL sin theta. This is the expression for force that a conductor will experience if it is placed in a uniform magnetic field inclined in angle theta. In vector form, if you write this, force, we put arrowhead in vector form. This I and L, current in a direction in a particular conductor, we take this vector cross B. This is in vector form. IL cross B is ILB sin theta. So this is the representation in vector form. Now, special cases will arise here depending upon this angle at which the current and the magnetic field, or we can say the velocity and the magnetic field, are making the angle. It's basically not the velocity, it is the current, direction of current and magnetic field. Let us see some special cases. Case 1, when current and the magnetic field are making an angle, right angles, they are at right angles. In that case, you get F is equal to IBL sin theta, sin 90 degree. Right angle with theta is 90 degree, then will be IBL, you will get maximum force. Sin 90 is equal to 1. So we write it as IBL, then we'll get a maximum force. That means if I allow the magnetic field to pass perpendicularly like this with the direction of current, then the force experienced by the conductor will be maximum. And if I and B are parallel or anti-parallel, if they make an angle of 0 degree, if the magnetic field passes like this along the direction of current, then the angle will be 0 degree. Case 2, when I and B are parallel to each other, that is when theta is equal to 0 degree, then the force experienced will be 0 or minimum, we can say IBL sin 0 degree, IBL sin 0 degree, sin 0 degree is equal to 0, so it will become IBL since sin 0 degree is equal to 0. Or case 3, when they are anti-parallel, suppose magnetic field is passing this way and electric current you are allowing it to pass in the opposite order like this, in opposite direction, then case 3, when I and B are anti-parallel to each other, that is theta equal to, when they will go in this direction, I is this side, current is flowing this side, magnetic field is going this side, then angle between them will become 180 degree. Theta will be 180 degree, and if it becomes 180 degree also, the value of F, the value of force here in the earlier case is 0. Everything will turn out to be 0, because sin 0 degree is equal to 0. Sin 180 degree is also equal to 0. Sin 180 degree is also equal to 0. Minimum force will be experienced. That means to make a conductor to experience some force in a magnetic field, if an angle is formed, if it is like this theta or like this, also force will be experienced by the conductor. This side also force will be experienced by the conductor, but it should not be 0 degree. The angle should not be 0 degree. Both the vectors B and I, if they are in the same direction, then either in the same direction or in the opposite direction, then the angle, the force experience will be 0. The force experience will be 0. It must be perpendicular, then you get maximum force. I and B must be at right angles. It must intersect at 90 degree to get maximum force. Now, if a conductor placed in a magnetic field experiences force, then in which side the conductor will move? That one to know, we use a rule called Fleming left-hand rule. This one you have studied in grade 10 as well. Fleming's left-hand rule. This rule will tell you, practically when you do, stretch your forefinger, the middle finger and the thumb at right angles to each other, mutually at right angles to each other. If the forefinger points towards the direction of magnetic field, and the central finger points towards the direction of electric current. Then the thumb will show the direction of the conductor or the motion of the conductor, which side it will move. Let us do and see. Suppose magnetic field line is passing this side. This is the conductor, suppose, or let me take the marker is the conductor. This is a conductor. I am allowing current to flow in this direction. So I will keep it like this. Magnetic field is in this direction towards you. It is going this side towards you. Then the conductor will tend to move, and that will be shown by the thumb. The conductor will tend to move in this direction, upwards. This will try to move upwards. The thumb will tend. If it is like this, suppose conductor is like this, current is flowing this way, and then magnetic field line is showing this side, moving from north to south, this side, then the conductor will tend to move in this direction. The thumb will show the direction, which side it should move. That forms the principle of electric motor as well. If magnetic field and electric current are right angles to each other, then the conductor should show some movement, and that movement is shown by the thumb. You can do in any way and check it out. This way you can rotate it, this way you can turn, this way you can turn, but make sure that these three are at right angles to each other. You can use your wrist to rotate and get the exact direction which side it should move. Now let us see the force between two parallel wires. Carrying currents. Now in this case, we'll take two infinitely long parallel wires like this, separated at a distance r from each other. This is wire 1. Let us mark this wire 1, and this is wire 2, second wire. Now I am allowing current I1 to pass through wire 1 and current I2 to pass through the second wire. Now to find out the force experienced by the second wire due to the first wire, what you'll have to do is, you'll have to find out the magnetic field at a point, suppose say P, in the second wire due to the first wire. So it will go this way, the magnetic field. You don't have to draw this circle, but you should know that at that point the field is passing. So what will be the magnetic field at point P due to wire 1? That you have to first find out the magnetic field strength. Like this, I'll write down, let two wires or two infinitely long wires be placed at a distance r in vacuum, or placed in vacuum at a distance r, placed at a distance r, be parallel to each other. Be parallel to each other. Let I1 and I2 be the currents flowing through the wire 1 and 2 respectively. So first of all, the magnetic field at point P on the second wire due to the first wire, that we'll find out. Like this you can do. The magnetic field at P on the second wire or on the wire 2 due to wire 1 is, let us write it as B1. This is due to wire 1. So magnetic field due to a long straight conductor of infinite length, we have come across before while doing Ampere's capital law. The formula is mu naught I divided by 2 pi r. This is your formula, and this is because of which current? Distance is r. Okay, we have taken r. This is because of current I1. So here I will write I1. Then after getting the magnetic field at point P, now you can find out the force experienced by wire 1 due to the presence wire 2 due to the presence of wire 1. Therefore, the force experienced by wire 2 due to wire 1 is wire 1 of unit length. We'll take of unit length your expression for force. This is force experienced by the second wire to the first wire. This will be V1, the amount of current flowing, that is I2, and the length of the wire, unit length. This unit length, this is the value is 1. So this is BIL. Now V1 we have found out here, mu naught divided by 2 pi r, current I1, and this is I2 per unit length of the wire, L per unit length of the wire, L. Its magnitude is actually 1. So we can write this as F21 is equal to mu naught divided by 4 pi. If I take like this and multiplying by 2 downside, then on top also multiply by 2. I1, I2 divided by R, the distance between the wires, and L value here is 1. Since L is of unit length, its value is 1. So this will be the force experienced by the second wire due to the presence of first wire. Now the force experienced by the first wire due to the presence of second wire also will be the same. Magnitude will be same, because here again you will find out the magnetic field because of this second wire. You draw the circle like this. Then after that you will find out the force experienced by it using this formula BIL. So the result will remain the same. But here you need to be very careful. The direction, that is more important here. When this at point P, the direction of current is going up. The direction of current is going up, and then it's coming like this. The field direction, when the current is coming down from down to top, then the magnetic field line is circular. We know it will be anti-clockwise. This anti-clockwise, like this is going, like this. This way it is coming and going. This is the wire, like this it is coming. Then at that point, at point P, it is flying over tangentially. This way it is going on. Here it is more making an angle of 90 degree with the radius. This is the direction of magnetic field, that is B1. So going inwards. So when you use your Fleming's left hand rule, the current direction, this is your current direction, it is going up, like this, like this it is going up, current is going up, magnetic field is going inwards this side, then the force will be towards the wire, it will be towards the wire. This F21 is towards the wire. Like this, when you look at this wire, in this case, it is towards the first wire, direction is towards the first wire. It's coming like this. Now, if the force experienced by wire 1 due to the presence of wire 2, let us see, the force experienced by wire 1 due to wire 2 of unit length. Here the formula F12, it will become B2, I1, and then ultimately B2 will be this one I2, mu naught I2 divided by 2 pi r, mu naught I2 divided by 2 pi r, then this I1 will come here in L. It will remain the same, only that the magnetic field will have to start from here. The magnetic field at, let us say it is Q then. The second part also let us do it as Q. On the wire 1, due to wire 2 is, suppose say B2. If we mark it as B2, then it is because of current I2, so it will be I2. Now the force experienced by wire 1 due to wire 2 of unit length, it will look like this. Force experienced by wire 1 due to wire 2. B2, this one B2, current flowing through it is I1, in the first wire it is I1 into L. So if you put the value, it will look the same, everything you will get as it is, it will remain the same, but the direction will change. In this case, the field is like this, it is like this, current is coming from down, still it is anti-clockwise, but when it comes here, it will fly over tangentially towards you. It's coming towards you. So field direction is coming towards you like this, and current is flowing from bottom to top. So the force will be shown by the thumb. It will be towards the other wire. It is coming towards us or towards you. This is B2. Then the direction of force F12 will be towards the second wire. Towards the second wire. So now what we can understand here is, if we allow the current to flow in the same direction, the force is coming together like this, they will attract each other. One wire is attracting the other wire, one wire is attracting the other wire. So there will be force of attraction. So we can conclude like this. These are the mathematical expressions for doing numericals. Then when two parallel wires the currents are in the same direction, they attract each other, and when they are in opposite direction, they repel each other. The magnitudes will remain the same, but magnitude of force will remain the same, but they will repel each other. If suppose current I1 I am passing from down and I2 I am passing from top to bottom here, opposite direction, then the whole thing will change. These force directions will change. Here it will go this way, and this one will go on the other direction. F12 you will get it. This one you can think and see. If they are opposite to each other, you can use your Fleming's left hand rule and you can find out that the two forces will be in the opposite order and then they will repel each other. Two forces, two wires are going like this, that means they are repelling each other. You can find out. With this formula, the magnitude of force, the unit of electric current ampere is being defined. Let us define and see now what is 1 ampere. Or how do you define ampere? Definition of ampere. An ampere is defined as that current or you can say 1 ampere is defined as that current which when two parallel current carrying conductors placed of infinite length placed in vacuum produces a force of 2 into 10 to the power minus 7 Newton per meter length of the wire, per meter length of the wire. It says like this: if two parallel wires, you are allowing current to flow through it, and if they attract each other or repel each other also will do, if they produces a force equal to this one. Force can be force of attraction also, it can be force of repulsion also, as we have seen, depending upon the direction of current. If they produce this force 2 into 10 to the power minus 7 Newton per meter length of the wire, if they can produce that force, then we'll say that the current which we are passing through the wire is of 1 ampere. You can show mathematically like this. It is coming from this formula. If I1, I2, we need 1 ampere. So suppose this is 1 ampere. Then per unit length, here unit length, we have already taken 1 here. Suppose length of the wire, we have taken 1. And kept unit distance apart from each other. Did I write or not? See, an ampere is defined as that current which when two parallel current carrying conductors of infinite length placed 1 meter apart. It should be 1 meter apart in vacuum. 1 meter apart in vacuum produces a force of this value. So here distance r is equal to 1 meter. Then if you put it in the formula for force, mu naught divided by 4 pi 2 times I1 I2 divided by the distance r into L. L is also 1 here. If you put these values 1, 1, 1, 1, that all become 1, only 2 will remain. Mu naught divided by 4 pi into 2. So it will become mu naught by 4 pi, your value is 10 to the power minus 7 into 2. Or we write this as 2 into 10 to the power minus 7, the order we write later. And force unit, we know that it is Newton. So when the current flowing through them is 1 ampere each, then the force of attraction or repulsion should be this value 2 into 10 to the power minus 7 Newton. This is how it is defined, 1 ampere of current. Let us see now torque experienced by a current loop placed in a magnetic field. Suppose, let us take like this a rectangular loop. Generally in class of grade 10, you studied this as electric motor, 2 commutator rings, carbon brushes. But here you don't have to focus now. Here it is rectangular loop. Suppose you are sending current through it. Carbon brush. This is your key and this is your cell. Current is passing in this direction. This rectangular loop, when you are placing it in a uniform magnetic field, suppose this is the north pole of the magnet, north pole, and this is the south pole. Here we will be studying basically about the motion of the conductor or motion of the loop. Let us take this loop as A, B, C, D. Let the current flowing through it be I. Magnetic field, it is in this direction. This is your magnetic field. This B is different. Let me write it as P, Q, R and S. Current I is flowing through the loop like this. I write like this. Let PQRS be a current loop, rectangular current loop, placed in a magnetic field. This placed in a magnetic field. These two are the pole pieces of the magnet. Let PS is equal to QR. Let us take it as A. This breadth is suppose A, and this length we can write here. We'll take it as B. Suppose the length of the conductor is B. You can take it here also, or outside also you can take. And let PS QR equal to A, and PQ is equal to Rs. Suppose the breadth is B, length is B. Case 1, when the plane of the loop is in the direction of magnetic field. This is the plane. Suppose if this is a rectangular loop, then this is the plane of the loop. Like this it is kept. Magnetic field is passing this way. So magnetic field direction and the plane of the loop, they are making an angle of 0 degree. And the plane of the loop is in the direction of the field. Direction of the field. So in this case, if you take the front part of the loop, PR, QR, we know that here this QR direction of current QR and SP, they are parallel with the magnetic field. One is parallel, one is anti-parallel. So in both the cases, QR will not show any movement, will not produce any force, it will not have any force. PS also will not have any force as they are parallel to each other with the magnetic field. One is parallel and one is anti-parallel. So they will not produce any field. But these two sides, PQ and RS, they are perpendicular. Current is going like this and magnetic field is passing in this direction. So they are intersecting each other at an angle of 90 degree. So this side PQ will experience some force. The same way here also, current is coming down, magnetic field is going from left to right, this side, from left to right. They are intersecting each other at an angle theta. So this side RS also will experience some force. In this case, when the plane of the loop and the direction of the field are together in the same, the direction of the field is along the plane of the loop, we can draw this way. Suppose this is Q, this end I am drawing Q, this is R. I can divide the loop into two parts. Suppose this is center of the loop, that will be O. Then this part will become the weight. Let us take it as mg acting downward. Then this part, whole thing QR was A, so it will be A by 2. This also will become A by 2. This end, if you use Fleming's left hand rule, magnetic field is in this direction, current is flowing in the, magnetic field is in this direction, current is flowing up, current is flowing up, current is flowing up, magnetic field is in this direction, then the side PQ will move downwards. Here the force experienced by PQ will be downwards. Here this end Q, I am drawing downside F1, experienced by this side PQ. And the other side, magnetic field is going in this direction, current is coming down, so RS will move in the forward direction, it will come towards you. So it will be in the forward direction, upward direction it will have. So I will draw this way, F2. Like this you can take it. And I will write down about this. There will be no force experienced by the wires or the sides QR and SP as the angle between B, there is the magnetic field, and QR or SP is equal to angle between B and the current, I can write, and the current are 0 degree and 180 degree. So there will be no force experienced by this side QR and SP of the wire. The force will be experienced by side PQ and RS. That will mention it now. The force experienced by wire PQ, first of all, from the arm PQ is F is equal to BIL sine theta. Sine here it is 90 degree. Angle between the current direction and the magnetic field is 90 degree. Here you get 90 degree. So it will be BIL sine 90 degree is equal to 1. So it will give you BIL. And what is L? The length of the conductor we have chosen as B here. So in place of L it will be B. Since L is equal to B. So it will be B. Now after finding out the force, the torque experienced, this is for one side of the wire. The other side of the wire also will experience the same force BIL, that is RS. The force experienced by RS is F is equal to BIB. Let us write this F2. We are mentioning it as F2, the other part of the wire. This one is F1. You will get the same result, F1 and F2. These two forces, F1 and F2, they are acting in the opposite direction. If we use our Fleming's left-hand rule, we find out that this PQ moves in the downward direction and RS moves in the forward direction, up direction. So these two equal and opposite forces forms a torque, or a couple is formed, which will tend this rectangular coil or rectangular loop to rotate couple. Therefore, the torque experienced by it, torque if I write this is R cross F, perpendicular distance, cross product of perpendicular distance and force. Now your perpendicular distance here it is for half part it is A by 2. This one you can use RF sine theta. Theta here it is 90 degree. Theta here it is 90 degree. Current and magnetic field direction is 90 degree. So it will give us 1 RF. So this one R into F. Half part if I take A by 2 into F, force is F1. We are writing F1 plus the other half A by 2, force we are writing it as F2, and the magnitudes are here BIB. So A by 2, we can take it common, F1 BIB plus F2 BIB. So it will give us 2 times BIB. So 2 and this 2 will get cancelled. So ultimately you will get BIA into B will become AB. And AB is called the area of the loop. This PQRS, this area of the loop. We'll write it as BIA. Here A is equal to A into B. The breadth and the length of the rectangle. Length into breadth gives us area. This line that we are drawing, better write it as N, or normal direction. R is written as normal direction. It's perpendicular with the plane. So next case, when we will tilt this QR slightly like this, then this normal must remain normal with the line QR, or with the side of the rectangle QR. Now let us see case 2. When the plane of the loop is at an angle alpha with the direction of magnetic field. Now also the magnetic field will not change, it is passing straight. This was the direction of magnetic field in this diagram. Now it will remain the same, the direction of magnetic field. Only what you are doing is this plane of the loop you are tilting, like this you are making it. This side is coming up, this is going down. So if this is the plane, it is slightly coming like this. Then what will happen if you draw the diagram like this? The direction of magnetic field will remain the same, B will remain the same, only this is tilted, this is going up, so it will come like this. So the forces direction F1 and F2 also will remain the same. What will change is this normal, now this is tilted, it's not like this. This has gone down a little bit and this one has gone up. This length of the wire QR also will remain the same, QR. This is still A by 2, A by 2 you took, because total length was A. So now it is A by 2, A by 2 will remain like before. And then this one was your normal, perpendicular to the plane of the loop. Earlier it was also 90 degrees, now also 90 degrees, just tilting. So this time the direction of the current, the plane of the loop and the magnetic field is tilted by some angle. Let us say it as alpha here. If this is alpha, the vertical opposite angles are equal, this angle also will be alpha. And this right triangle, if you take, you can find the perpendicular distance to find the torque. To find the torque, you can do like this. This perpendicular distance, how we find out in the right triangle, this angle is alpha, this is the acute angle, so this will become the base, and this is your hypotenuse. So it will be A by 2 cos alpha. And the same way here also, this is the base, this is the hypotenuse, this is 90. So it will become A by 2 cos alpha. This is the direction of magnetic field. It is still the same. So the perpendicular distance you can find like this. So when the plane of the loop is at an angle alpha, or theta also you can take, the direction of the magnetic field. In this case, the torque is equal to force into perpendicular distance, or perpendicular distance into force. If you use the perpendicular distance, here you can see for force F1 it is A by 2 cos alpha, A by 2 cos alpha into force is F1, plus for the second half perpendicular distance is A by 2 cos alpha, A by 2 cos alpha, and force is F2. So the magnitude of F1 and F2, as you know already, it is BIB. If you put it here, both will get the same thing, 2 times A by 2 cos alpha. I'm doing twice the same thing. The force is BI, B. So this one 2, 2, if you cancel it out, you'll get BI, this one A into B, AB cos alpha. Then this will be BI A, the area of the coil, cos alpha. This will give you the expression for torque, which is inclined at an angle alpha with the direction of magnetic field. And if the loop has n turns, instead of one single turn, if the loop has many turns like this, then the torque experienced will be given by n times BI A cos alpha. This can also be written as tau is equal to this NIA is also known as magnetic dipole moment M B cos alpha. Like this you can write down. M is equal to NIA is called the magnetic dipole moment. Magnetic dipole moment. So in this case, you can write torque expression as M dot B, dot product of magnetic dipole moment and magnetic field. If you write in vector quantity, because M dot B is MB cos alpha. Now, this one force means either force, any of the two forces F1 and F2. It can be either of the force. In this case, sometimes you may think like, while taking the force, the formula we got BIB. In finding out the expression for force, it is BIB sin theta. This angle theta and this angle alpha is completely different. This angle theta is the angle between the field line and the arm. The arm field line is passing from left to right like this. The arm, it goes like this, then also it will remain 90 degree. If it is like this also, it will remain here 90 degree. That's why the expression of force, we wrote BIB sin theta is 90 degrees, so it is equal to 1. So it is BI B. In both the cases, the expression for force, it will be BI B. Now here you need to be very careful whether sometimes you can use here sign also. If in the numerical, if in the question is given that the angle between the direction of magnetic field and the normal, that you can see here, normal is there. If this is given as theta, suppose, if this angle is given to you theta, then what we'll do, here sine will come. Let us write down and see. The angle between the normal and the magnetic field direction is theta, then in that case your formula becomes like this: torque is equal to NBIA, or you can remember it as BINA, the name of the person, Bina. Then cos alpha, in your formula it is cos alpha. Cos alpha is equal to 90 degree minus theta. 90 degree minus theta. So in this case, you get like this: BIA sine, if you write cos 90 minus theta, your complementary angle which you learned in grade 10. Cos 90 minus theta is sine theta. Like this also you can write but you need to be very careful in doing the numericals whether this angle is with the direction of the magnetic field and the normal, or between the plane of the coil and the direction of magnetic field. That you need to be careful when to use cos and when to use sine. And this also can be written as torque is equal to NBIA. The NIA, this is your magnetic dipole moment. So M will write to B sine theta. And in this case, in vector form, if you write, you can write it as M cross B. You can see here very clearly. You can use even cross product, you can use even dot product. But dot product we use if the angle is between the plane of the coil and the direction of magnetic field. But sine will use when, or cross product will use when the angle is between the normal and the magnetic field. So both possibilities are there. Thank you and have a nice day. Stay tuned with NFI Educates.